We are going to talk a little bit now about regression. And let me say that regression and correlation are closely related procedures. The emphasis in regression is on predicting scores on one variable from those on one or more others. We can do regression either with using z-scores, which is to say standardized scores, or using raw scores, which is to say scores that have not been computed to z-scores. So we're going to begin with looking at regression, which is to say prediction, using z-scores. And I'll just mention that as we discuss regression here, we're presuming that both variables, which is to say that the independent and the dependent variable, are numeric. And the regression prediction is prediction according to a straight line. So actually we're dealing with linear regression here. Towards the very end of the book, we'll talk about regression where either the independent or dependent variable may not be numeric, and also we'll deal then with regression where there is more than one independent variable. So the regressions that we're looking at here are bivariate regressions in the sense that we have one independent and one dependent variable. So here is our standardized regression equation. So the idea is we know the z-score on x, and also we presume that we know the correlation between x and y. So that if we know the z-score on x, and if we know the correlation of x on y, then for a given case, what is the best prediction of that case's z-score on y? The little caret or hat symbolizes a predicted value. And the standardized regression equation tells us that the best prediction of a case's z-score on y is found by multiplying that case's z-score on x by the correlation between x and y. And again, the notion here is that we know the correlation, we know the z-score on x, we don't know the z-score on y. We want to make a prediction of that z-score. So here's an example. Ann's z-score on self-esteem equals 0.90. That z-score is greater than 0, so Ann's score is above the mean on self-esteem. Now further, the correlation of self-esteem and stress in daily life is found to be minus 0.60. In other words, a reasonably strong negative correlation. Let's make our best prediction of Ann's z-score on stress. So what we do is we take the correlation between x and y, which is to say between self-esteem and stress, and we multiply that by the case's z-score on x. So the correlation times Ann's z-score yields a predicted z-score on y, z-score on stress of minus 0.54. So let's get some practice here. Here's our standardized regression equation. Let's use it to make our best prediction of a case's z-score on y. So here's a first example. The case's z-score on x is 1.6. The correlation between x and y is 0.5. What's the predicted z-score on y? So we multiply 1.6 times 0.5 and we get 0.8. So in this first example, our predicted z-score on y is 0.8. 8, that is to say we predict that the case's z-score on y will be 8/10 of a standard deviation above the mean. Let's go ahead and take a look at this third one. So here, z-score on x is minus 1.6. The correlation is 0.5. So we would multiply together and we would get minus 0.8. A predicted z-score on y that is 8/10 of a standard deviation below the mean. And let's go ahead and do this fourth one here. Minus 1.6 times minus 0.5 would yield 0.8. So the correlation here is negative, the z-score is negative, and we predict a z-score on y that is 8/10 of a standard deviation below the mean. And finally, let's do this one. So what's of interest here is that the correlation between x and y is 0. So actually, as we multiply 1.6 times 0, we're going to get a product of 0. So, we talked a little bit about it, but, a correlation of 0. And we accepted the case of curvilinear relationship. But in terms of linear relationship, correlation of 0 is conveying absolutely no relationship. So when there's a correlation of 0, the best prediction that you can make for a given case is that the z-score on y will be right at the mean, which is to say 0.00 is a z-score exactly at the mean. It's a little more on what R is conveying to you. One of the meanings of R is that R is conveying to you the predicted change in standard deviations in y as x increases by 1 standard deviation. So, to give an example of what we mean, suppose that you have computed the correlation between highest grade of school completed and income, and that correlation, which is to say R, comes to 0.40. So one of the meanings of this correlation is that as grade completed increases by 1 standard deviation, income is predicted to increase by 0.40 standard deviations. As another example, perhaps the correlation between self-esteem and depression is minus 0.55. So this conveys to you as self-esteem increases by 1 standard deviation, depression is predicted to decrease by 0.55 standard deviations. The correlation here is negative, and so we predict a decrease. And I'll just make a note. Correlation in some senses is bidirectional. It works both ways. But it really only works both ways if both of the involved variables are such that neither is clearly independent and dependent. So let me go ahead and interpret this correlation of minus 0.55 differently. So we could also say that as depression increases by 1 standard deviation, self-esteem is predicted to decrease by 0.55 standard deviations. So I reversed the description of the variables there. So correlation is bidirectional in that sense. But think about this top example. Here, it's clearly the case that grade of school completed is your independent variable, and income is your dependent variable. And since we've got straightforward independent and dependent variables, it really only makes sense to talk about the relationship in a given direction, and that's the direction that's presented here. So, I mean, it's formally correct to say as income increases by 1 standard deviation, the highest completed grade of school is predicted to increase by 0.40 standard deviations. But that's not helpful, because it's reversing and confusing the independent and dependent variables. We've talked about the fact that R is conveying linear relationship between two variables. So question comes up, and this relates to the exception that was noted in the prior video. Does an R of 0 always convey the absence of association between two variables? And the answer is no. So what an R of 0 is conveying is the absence of linear, straight line relationship between two variables. So indeed it is possible to have an R that equals 0 or is extremely close to 0, and that the two variables are indeed associated. The two variables would not have a linear association, but it is possible that R could be 0 and the two variables would have a nonlinear association. The key way in which variables might be related in nonlinear fashion is curvilinear relationship. So curvilinear relationship is relationship that is best described by a curve. So let's think through an example of a relationship that might be curvilinear. So here we're thinking about the relationship between hours studied to score on an exam. So scores on an exam might range from 0% to 100%. Or perhaps no one gets a 0, in which case the range is less. But let's think through this relationship. As one begins to study, this helps their grade greatly. In other words, people who study not at all, 0 hours, almost without exception, are going to get very low grades. Now, as you do some studying, this is going to help. I mean, particularly to do some moderate, basic amount of studying, that perhaps is going to help a great deal. And certainly studying hard and long is going to help a great deal. But, you know, at some point, one could push too hard in their studying. As they would study more and more hours, they would learn less and less. Not to mention would they learn less and less, but they would get increasingly tired and increasingly stressed out, and perhaps more and more anxious about the exam. So if you picture persons studying and studying and studying and not stopping studying, at some point, as they study more and more, the best prediction is that performance on the exam will worsen. So this is an example then of curvilinear relationship. Hours studied is low. As you study more, exam scores go up. As hours studied gets to be too high, study ceases to help, and then as hours studied gets higher still, the relationship between hours studied and score on the exam, actually becomes a negative one. So here's another example, hypothetical one, of a relationship that I would guess would be curvilinear. So we're trying to look at the level of flexibility in a family, perhaps with respect to setting rules for kids, and just in general, sort of the level of structure in the family. Is there no structure at all? In which case, in essence, there's perhaps chaos, or is everything overly structured, right to a T? In which case things are very rigid with no room to give. And so then somehow we have a measure of the social functioning of that family. I mean, how well do people in the family get along? Perhaps it relates also to how do people in the family relate outside of the family context. We'll leave this social functioning undefined. So here we have extremely low flexibility, in other words, total rigidity. And you can see that the dots in our scatter plot are low on the y-axis. So social functioning is quite low here. Now then we're moving up into middle levels of flexibility. So these families have consistency, guidelines, rules, but they also have the ability perhaps to adapt to different situations and to shift those rules some when necessary. So what are our social functioning scores for families in this middle level of flexibility? And you can see the scores are high on the y-axis. So on this left side of our slide then, the relationship between flexibility and social functioning is largely a positive one. As flexibility moves upward, from low to medium, social functioning tends to increase. But you can see that this pattern of dots in the scatter plots takes a turn towards a downward trend as we move above middle levels of flexibility. So in other words, as we get to the very, very highly flexible families, the social functioning is again low. So here what you have in essence is a situation of chaos, no rules at all, and certainly it's hard to function well in this situation. So now I guess as I really look closely at this pattern of dots, it looks more like an angle than a curve. And it is indeed possible to have a sharp bend as is depicted here. But I'm going to really try to more convey that the real pattern we have here is this curve. So we do have relationship, which is to say we can see pattern. We don't have that buckshot scattering of dots that we had when we looked previously at a correlation of 0. So this is an example of a situation where the correlation between flexibility and social functioning as measured by R actually is very close to 0. I think I did go ahead and calculate the correlation between these two variables as depicted here in this scatter plot, and R came to minus 0.02. So R was extremely close to 0. So in essence what you have here, is absence of linear association. So that's what R is telling you. But an R of 0 doesn't tell you necessarily that there is total absence of association, because you can indeed have an R of 0 or close to 0 and have a nonlinear relationship. Most often when that is so, you're going to see curvilinear relationship. And I will add that it's usually a good strategy, particularly if you suspect curvilinear relationship, to go ahead and have your computer software program create the scatter plot for you. And then you can go ahead and assess that relationship visually. So this next slide is really summarizing my concluding comments to the prior slide. I'll just let you take a look. An important new point is to see that indeed Pearson's R, when I say Pearson's R, I mean that is the R that's used again and again and again. I mean essentially almost always. And Pearson's R is not an appropriate measure for curvilinear or other nonlinear relationships. And so being an introductory course, I mean, I'm not going to cover in detail what is the best relationship for a measure of relationship in the curvilinear situation, but it is important that you know that R does not appropriately measure the degree of a nonlinear relationship.